Okay, so we talked about these characteristic curves, and what actually this equation does that we discussed is, as you can see, it carries out the information from the initial condition to by two traveling waves, one which is moving to the right and one which is moving to the left. And so what it does is that the initial condition splits into two waves, one right and one left going, as you can see here, with du x and 0 over dt equals to 0. So this is what it does. The initial condition is split into two ways, one right and one left going. And with this condition, when your first derivative of u with respect to time is 0, then what you will have is symmetric waves under t. That is, anything is just symmetric around t and minus t, which is the time reference. As you see here, so here you see that we have this symmetry, right? So in the left and right, these two are symmetric, as you see here. So this condition occurs when your du over dx with respect to time is equal to 0 for this equation, okay? Okay, so this was an example that we solved to find how we can actually use this D'Alembert solution and find these two functions these two functions of fx minus ct and gx plus cd. How can we apply and add these initial conditions into these functions, right? And find the form of f and g here. Okay, so now I want to go talk a little bit more. So just I forgot, I think, to talk about this this thing, that how does this superposition looks like if you have something in between these two borders. So just to give you this very quickly, and then we will move to another example. So say you are in t, let me see if I can do this. Let me do it with another color. Okay, so say we have this, and then I'm gonna draw this line. Okay, and then one here to show. I want to show the progression of these equation and show how you can actually solve this at different times, and that is with superposition. Okay, so we have to superpose these two functions, which is these two ones that we found, u naught x minus t ct over 2 plus u naught x plus ct over 2, right? So let's see if this is t. So these are all t, sorry, these are x. And this is time. So this one, I'm going to show it at time equals to 0, just the top plot. So let's look at what does this look like. So you have this function. This is half of the u naught at x at t equals to 0 plus the other one, exactly the same one. And so if you add these two together, that is like you have to multiply this by 2, you are gonna get something like this, right? So here is 1, and here is also 1, and here is minus 1. Okay, so I want to say what happens as we go further in time. Okay, so let me draw this. So what's gonna happen is we just continue this, and then this one too. The same thing here for the other one. And these. So these are two lines, right? So, and I want to do also something in between, so you get to know how does this look like. So if you are, say, here, let me do it here. No, a little bit like I want to have what happens when you are in between these two limits. Okay, so here what you are gonna have here is, say, so let's first go to the last one. So the last one is when t is greater than 1 over c. So what you are gonna see is similar to what I plotted before, right? So this is gonna be the solution for ux minus u naught x plus ct, and 1 is gonna be ux u naught x minus ct. Okay, so these two. So here, this is gonna be my solution here. For any t that is here, this is gonna be my solution. And then let's see when we are here, what's gonna happen. So here, t is between 0 and 1 over c. Okay. So let's see what's gonna happen here. So when we are here, we are gonna have something like this. So we have two waves. One here and one here, right? So these are gonna superpose. So we have to superpose these two waves, and so what we are gonna get is something like this. So the solution here would look like this blue line that I am drawing. Okay, and the solution here is this one. So this is the progression of the solution. So here when you are, this should be symmetric. So here, when you are between these two limits, you just have to superpose these two solutions together. And then after that, when your t is greater than 1 over c, then these two waves will be completely separate from each other. Okay, so this was just one remark that I wanted to make. And now I want to move forward with another example, which is again similar to finding the characteristic waves, but I want to find it from another way, which is by solving a matrix. Okay, so the example here states find the characteristic curves for the following wave equation. Okay, so let's see, this is let me write it again. So it is actually the following dynamic wave equation. So this is the dynamic wave equation. Okay, so this is dy d partial y partial t plus capital U d partial u partial y partial x plus y partial u partial x equals to 0, and then du over dt plus du over dx plus g, which is a gravitational constant, dy dx equals to 0. So we want to find the characteristic waves for this equation. Okay, so what I'm gonna do here, this technique, the first technique that we use for transport equation, an advective transport equation, I'm gonna use that technique here to find the characteristic curves for this equation. So y can be a function of x and t. So y is a dependent variable, and x and t are independent. And so I can write dy equals to the total difference of y can be written as the difference of dx and dt. So I can write partial y partial x dx plus partial y partial t dt, and then write, similar to that, I just write just rearrange the terms and write partial y partial t equals to dy dt minus dx over dt times partial y partial x. Okay, so I'm gonna name this equation equation 1, and then for u, again u is a dependent variable and x and t are independent, so u is going to be a function of x and t, which is space and time. And so I can write it down similarly. I can write an equation for du dt partial u partial t equals to du dt minus dx dt times partial u partial x. Okay, so this I'm going to write it as equation 2. So what I'm going to do now is I want to substitute 1 and 2 into dynamic wave equation. So what I'm actually gonna do is I'm gonna substitute these two into this equation, okay? For the partial u, I have this this equation, this term, and this term, right? So I'm gonna just substitute them here. So let's see what do we have. So the first one is gonna be dy dt minus dx dt d partial y partial x plus u partial y partial x plus y partial u partial x equals to 0. Okay, and I want to rearrange this, so I'm going to rearrange it into this dy dt. I'm just going to factor partial y partial x, so I'm going to get u minus dx dt partial y partial x plus y partial u partial x equals to 0. So the second equation, I'm gonna substitute partial u partial t in that. So I'm gonna get du dt minus dx dt partial u partial x plus u partial x plus g partial y partial x equals to 0. And I'm gonna again rearrange this factor partial u partial x and write it down as du dt plus u minus dx over dt partial u partial x plus g partial y partial x equals to 0. Okay. So this is the equation, these two equations that I have now, which are the new equations. And what I want to do now, I want to, because they kind of look similar, I want to write these into matrix form. So write these in a matrix form. Okay, so let's get started. That's how I want to do this. This is the matrix. So the first one here I want to put is partial y partial x, and the second one is partial u partial x equals to, okay, so let's first see what are the in the first equation the term for partial y partial x. So this is the term for partial y partial x in the first equation, and this is the term for partial y partial x in the second equation. Okay. And this is the part for partial y partial u partial x in the first equation, and this one is for partial y partial x. So in the first equation, let's write it here. The partial u partial y partial x, what should I put here? This should be u minus dx dt, right? And then we have the second term, which is y dy partial u partial x. So I'm just going to put here y. And then we have the third term, which is the dy dt, right? So I'm just going to write it minus dy dt. So this is coming from this equation, the first equation. Okay, the first line. And then let's go to the second equation. So the second equation, I have dy partial y partial x. So the term here is g that I have to put. And the second one is partial u partial x is u minus dx over dt. And then the last one is the time derivative, which is going to be du dt. Okay, so this, I just put this into a matrix form. And we cannot solve this matrix for partial u partial x and partial y partial x and partial u partial x if the determinant of this matrix is 0, right? So the determinant, if this is A, matrix A, if the determinant of A is 0. And this is the condition that defines the characteristic waves. So what you need to do in any type of PDE, especially linear PDEs, you need to find this kind of matrix and then solve for this matrix and say what is the condition that we cannot solve for dy over dx and like partial y partial x or partial u partial x, these kind of variables in your system, and then take the determinant of that matrix and find the characteristic curves. So let's do this here. So if we set determinant of A is gonna be u minus dx dt square minus gy equals to 0. This is coming from that matrix. And thus, this is going to give me u minus dx over dt is going to be plus minus square root of gy. And hence, dx over dt is going to be u plus minus square root of gy. Okay, so this is a final solution. And these are actually the characteristic waves of this problem. So this gy, we call this c, or wave celerity, wave speed. And this plus and minus show that we have two sets of characteristic lines, right? So this is square root of gy. This is a very important concept in hydraulics engineering and even hydrology, hydrodynamics, because this is the speed of water, especially if you have like a tank of water and then you release it. So if a tank of water and you release it, like there can be here a gate, and then you just release this. This is gonna move with this speed. The water is gonna move with, if this is y, is gonna move with square root of gy. So this is the speed of the wave. also in coastal engineering, like ocean waves. When you have, if this is like the ocean surface, and here you have a wave, this wave, the speed of this wave is square root of gy, and this is y. Okay, so this is how the waves propagate. This is the actually water waves, how they propagate. This equation is for that. And now I want to draw these characteristic curves. Characteristic curves. Okay. So we are going to have two cases. The first case is when the velocity is between c, the speed of the is between the wave speed, wave celerity, which is the here can be like a speed of the a water wave, and 0. So we are going to have two characteristics here. So the characteristics are going to be u plus c, which is greater than 0, and u minus c, which is going to be smaller than 0, right? Less than 0. So now I want to plot these. So the first one is, let me plot it with this color here and here, and we are going to have two boundary conditions. So I'm just gonna show that. Okay, so this is gonna be x. Here is x equals to L. Here is x equals to 0. This axis is time. And so let's see how the solution looks like here. So we are going to have two characteristics. One is u plus c, which is a positive number. So let's look at this. I'm going to plot it like this. And then the second characteristic is gonna be, so let me first write which one it is. This one is if you have 1, and this is u plus c, so this is that characteristic. And then the second characteristic, let's see. So the second characteristic is gonna be, again, a minus, has a minus negative slope. Okay, so, and this characteristic, let me write it down here, is so this characteristic, let me write it for this one. Has u minus c, which is gonna be a smaller number, and this is 1. So this is the slope of the second one. Okay, so these ones are going this way. These waves are going this way. And the other ones, these ones are going this way. Right? So these are the characteristics. So here, say for this one, this point here, this is gonna have the information from this is gonna come from 2 points, one here and one here, right? So we are gonna have 2 initial conditions here that determine the solution of this point in the space. So here I can write this that this space, let me do it with this. So this space is what we call the domain of dependence for this point in the space, right? So this is where the information comes, and we can find the solution for this this parameter. Okay, and here you can have some region where you will have, for example, here, if you are in this region, okay, so you are not gonna get a solution to initial conditions, but what you are gonna get in this space here is you will need one initial condition and one boundary condition. And let's see what does this mean. So here one of your solutions come from here, so you have one initial condition, and then the other one comes from here, right? And this is the boundary condition, so you will have one boundary condition. So this is actually, this line here is your boundary condition, okay, at x equal to 0. And here is your boundary condition at x equals to L. So you can have a region in which you can find it here. So this region, let me draw it here. Parallel to the other ones. So this region is where let me do it with another color. You will need, for in this region you will need one boundary condition and one initial condition to find the answer. So for example, say this point, you have the initial condition from here, and then the boundary condition is gonna be from here, right? So this is that point. So the domain of dependence. So you will need one boundary condition, one initial conditions. In the red one below, you need only 2 initial conditions. So if I want to extend it, this is gonna be where you would need only 2 initial conditions here, up to here. And then the rest, the other one, you would need let me draw it with another color, maybe this one. And here you need one boundary condition, the left boundary condition, and one initial condition. Okay, so this is how you have to you can have the full solution of this equation, but this is only for one case, which is when u is smaller than c. But how about the second case? So the second case is when u is greater than c. So in the second case, so one thing I forgot, this case, we call this subcritical flow. This is just a name in hydraulic engineering literature or ground flow literature, all these in hydrodynamic. So when u is smaller than square root of gy, which is your celerity, wave celerity, then your flow is going to be subcritical. And this has some meaning because there is a important dimensionless number in fluid mechanics, which is as Freud number, which is u over square root of gy. And this is when this Freud number is smaller than 1. So, and if you had some hydraulic engineering course in your undergrad, you know what this means. And then the second case is the other case where our characteristics are gonna be both greater than 0, so we have u plus c is greater than 0, and u minus c is also gonna be greater than 0. And this is a case where we call this supercritical flow. This happens when your u is greater than square root of gy, or your Freud number, u over square root of gy, is greater than 1. And we have a critical flow where this Freud number is 1. And this is an important fluid mechanics concept where, for example, when you have a supercritical flow, you can have a hydraulic jump and then go to a subcritical flow. So just to give, for those who have taken hydraulics engineering course in their undergraduate, so a supercritical flow is usually a very fast fluid, and then through some instabilities it can turn into a subcritical flow. So this will be a subcritical and this will be a supercritical flow, and this happens through what we call a hydraulic jump. Just to give you a background, where do these equations come from and what do these equations mean physically? Okay. So let's look at the second condition where our characteristics are now both positive, unlike the other one in which one of them was negative. So let's see how does the solution look like here and what is the difference. Okay, so we have this one and we have here, so this is gonna be x again, this is gonna be time, this is going to be x equals to L, and this is going to be x equals to 0. So now we have two characteristics, so let me draw them. So the characteristics, this is gonna be the first characteristic. Okay. And we can just go on here for the other ones. And the second one is gonna be also a positive, has to have a positive slope, okay? So I'm gonna plot it. So this one is gonna also have a positive slope. So this one, you're gonna have 1 and u minus t, and the other one is 1 and u plus c. Okay. So these are two characteristics. So this is going this way, and these are also going to the right. So both of them are going to the right. And now let's look at the domain of dependence here, just to do a quick analysis. So if you are here, if you have any point here, you will need one boundary condition at the left, right? Two boundary conditions, sorry, you need two boundary conditions here. So here you don't need any initial conditions, right? Unlike the other one, you don't need any initial condition, and you just need two boundary conditions, which are these boundary conditions on the left. And then if you're, so any point here, for example, this point, right? This, let me just do another one, maybe. Like, let's say this point. This is one boundary condition, and this is the other boundary condition, right? So you would need two boundary conditions for any point here. And then let's go to the other one. And if you are here, anywhere here, then it doesn't matter, right? Anywhere here, you would need one boundary condition and one initial condition. So here, you would need one boundary condition and one initial condition. For example, let's say here, this point. Or let me do another one. Let's say this point. Yeah, let's say this point, okay? And even, or this is one boundary condition and one initial condition. Sorry, I made a mistake. So this is only for, let me redraw it, because this is only for one region, and one region we have two initial conditions. So here, yeah, here is where we need one initial condition and one boundary condition. Let me do it maybe with another color so don't confuse it. Okay, oh, oops. Okay. So in this region, you need one initial condition and one boundary condition. And then in this region, you just need two initial conditions. And let's see what this means. What does this mean? So here you need two initial conditions. So let's see. For example, this point, you see, you need two initial conditions. One at here and one at here. And any point in the yellow region, for example, this point, you need an initial condition and a boundary condition, which is coming from the left, right? So this is how you can classify the regions for this type of equation and this type of PDE, and how you can solve it. Okay, so this was the topic for today, and about the characteristic waves and characteristic curves and how we can use them to solve these type of PDEs. Especially we talked about traveling waves, right? So we first started with D'Alembert's solution, and then we showed this general solution of this equation, which is fx minus ct plus gx plus ct. We proved that is a solution for this type of equations, and then we showed that we showed an example in which we found these functions, the form of these functions f and g, using the initial conditions u0x and du over dtx. And after finding these, we talked about some of the properties of these equations, like how you should do this superposition in order to find the solution of this equation. And then we solved another example of a dynamic wave equation in which we used another method for finding characteristic curves, and that is by using this matrix form and solving it where we define characteristic waves based on the determinant of this matrix. We found two wave celerities, and we showed what is the analogy of this in physics, which is just a water wave. And then we drew the characteristic curves for two cases, when we have a subcritical flow where u is smaller than c, and a supercritical flow where u, or velocity, is greater than your celerity. And we define regions where we need boundary condition or initial conditions in order to get and find the solution of these type of equations. Okay, so next time I'm gonna generalize these characteristic curves and show you how you can find a general formula for these characteristic curves. And then after that, we are gonna use that to define and classify the three type of second order linear PDEs, and talk about, if you recall, talking about those elliptic, hyperbolic, and parabolic equations, and what do these mean. They are just based on these definitions of them are just based on these characteristic curves. Okay, thank you very much.